Swayam Prabha. Digital India. Educated India.
Hello friends, welcome back to the lecture series of BSc with Chemistry, Physical Chemistry Paper 4. This is lecture 2 of module 2. In this particular lecture, we will continue with our discussion on the Faraday's law of electrolysis, and we will continue first to see the numericals which are based on the Faraday's law of electrolysis, and then we will see the reversible and irreversible cells, and then further concepts. So, in continuation with our previous lecture, this particular numerical is on the lines of the second law of electrolysis, or Faraday's second law of electrolysis. Now, what is asked in this numerical? In this numerical, let us try to understand. In certain electrolysis experiment, 1.55 grams of silver were deposited in one cell containing aqueous silver nitrate solution. Now, what we need to calculate? We are supposed to calculate the mass of zinc deposited in another cell containing aqueous zinc sulfate solution in series with silver nitrate cell, and molar masses of zinc and silver are given, that is 65.4 gram per mole and 107.9 gram per mole respectively. So basically we need to calculate the mass of zinc deposited in another cell which contains the zinc sulfate solution and which is in series with the silver nitrate solution. So let us try to understand the half cell reaction. The half cell reaction for the formation of silver at cathode in silver nitrate cell is basically this, which is given here. So 1 mole of electron is giving you 1 mole of silver. So the mole ratio is 1 mole of silver upon 1 mole of electron. So that will be 1. So mole ratio is 1 in this case. Whereas the half cell reaction for the formation of zinc at cathode of ZnSO4 cell is this particularly. So you can see here that 2 moles of electrons are required to deposit or precipitate 1 mole of zinc atom. So the mole ratio will be 1:2 and therefore it will be 0.5. So the moles of silver deposited will be mass of silver deposited upon molar mass of silver. Likewise this 1 point, if I substitute the molar mass of silver deposited, that is 1.55 upon molar mass of silver, that is 107.9. So it gives me 0.01437 moles of Ag. Now from the Faraday's second law of electrolysis, I have this relation: moles of zinc deposited upon moles of silver deposited equal to mole ratio of zinc deposited upon mole ratio of silver deposited. Or in other sense, if I can put equivalent weight of zinc upon equivalent weight of silver, that way I have certain values regarding if I represent this equation in terms of mole ratio, that will give me that moles of zinc deposited, which is equal to 1/2 upon 1/1 multiplied by 0.01437. So it gives me that way the moles of zinc deposited is equal to 0.01437 multiplied by half, and which comes out to be 7.185 into 10 to the power minus 3 moles of zinc. And from this moles of zinc I can calculate the mass of zinc deposited. So mass of zinc deposited is equal to moles of zinc deposited multiplied by molar mass of zinc. So if I substitute the corresponding values, I get 0.47 grams. So the mass of zinc deposited in the ZnSO4 cell, solution cell, which is corrected to silver nitrate cell, is about 0.47 grams. In this way, we can utilize both the laws, Faraday's first law of electrolysis and Faraday's second law of electrolysis, for the calculation of the quantity of substance deposited, quantity of current required, quantity number of electrons required, or quantity of charge required. So depending on the information available, I can utilize the Faraday's first and second laws of electrolysis for these purposes. Let us move ahead. So now, after this concept of the Faraday's first law and second law of electrolysis, we need to understand the several fundamental concepts in electrochemistry in order to understand the various other aspects. So let us try to understand the concept of reversible and irreversible cell. Now, according to thermodynamics, any process is said to be thermodynamically reversible it will be reversible only if there is equilibrium at every stage of process. This is the basic condition from the thermodynamics point of view. That means the driving force is infinitesimally greater than the opposing force, and the process takes place in an infinite number of steps at extremely slow rate. Then and then only your process will be reversible, isn't it? Then and then only I can call that the process is thermodynamically reversible. Now a cell is said to be reversible if it fulfills the three conditions. Which are these three conditions? So which are given over here. Number one is if an opposing EMF is exactly equal to the cell EMF is applied. Okay, so the cell reaction stops in such case, and no current flows through the circuit. So the basic condition, the first condition is that if an opposing EMF is exactly equal to the cell EMF is applied, and the cell reaction stops and no current flows through the circuit. Secondly, if an opposing EMF slightly smaller than the cell EMF, then the cell reaction will proceed in forward direction, and a small current will flow a small current flows in the forward direction. And similarly, the third condition is that if an opposing EMF is slightly greater than the cell EMF is applied, the cell reaction occurs in the backward direction and small current flows in the backward direction. Diagrammatically, it is represented over here. So these reversible processes, they will be existing if these three conditions satisfy. In this case, the opposing current is exactly equal to the cell EMF, and therefore there will be no net cell reaction. Therefore, no current will flow through it. In second case, the opposing EMF is slightly smaller than the cell EMF, and therefore this small current in the forward direction will flow. And the third one is the opposing EMF is slightly greater than the cell EMF. If we apply, so cell reaction occurs will be in the backward direction, and small current will flow in the backward direction. So if you see here, the condition is given. So in this particular Daniell cell, if you see, this is the particular representation of Daniell cell. So if opposing EMF is slightly greater than the cell EMF, the reaction gets just reversed in this direction. Okay, this is particular reaction, and if I apply the EMF which is slightly greater than the cell EMF, so it will be reversed in this manner. Okay, let us try to understand the irreversible cell. So cell which do not obey the condition of thermodynamic reversibility are called as irreversible cell. So simple. So in case of irreversible cell, say let us consider an example of irreversible cell in which zinc and silver electrodes are dipped in H2SO4 solution. So the cell can be represented as this. So zinc and silver electrode in contact with the hydrogen ion from the sulfuric acid. So if the external EMF lower than the cell EMF is applied in opposite direction, this particular reaction occurs. Now in this reaction, zinc goes into solution liberating hydrogen gas. Okay. And secondly, if the opposing EMF is slightly higher than the cell EMF, this particular reaction will take place. That is, the silver goes in solution and hydrogen gas will liberate. Now since in this case the reaction is not reversed, it is called as irreversible cell. You can see here at anode this happens, at cathode this happens. Okay. Now the very important concept of cell representation. Basically, cell representation is an important concept one has to be understood, because it is a compact way of representing the cell composition. So the cell, uh, it consists of the two electrodes basically, and in cell representation, the anode is represented on the left side while the cathode is represented on right side, and any direct contact between the electrode and solution will be shown by the single line. while porous partitions by double line. Okay, and the reaction proceeds spontaneously from left to right, and therefore if I want to represent the Daniell cell, it will be represented as this. Okay, so if the cell consists of two electrodes, the electrode at which the oxidation takes place is known as anode, and it is negatively charged, and it will be always represented on the left hand side. Likewise, the electrode at which the reduction takes place is cathode, and it is positive, and it will always be represented on the right side. Now, when the electrode is in direct contact with the electrolyte, they are separated by single line, and porous partition or say salt bridge connection will be represented by double line, as I said. And if the concentration of the two electrolytes are shown in bracket, so if the concentrations are given, they can be shown in the bracket. Okay, say for example, let us take this example of Daniell cell, which is represented here. Okay, so zinc in contact with zinc ions, and this ZnSO4 of concentration 1. Now copper electrode is in contact with the copper ion, say copper sulfate, which is of concentration C2, and both of these electrolytes, they are connected by say salt bridge, and therefore it is represented by double line. Okay, so this is for direct contact, and this is for porous partition or salt bridge, and these two are representing the concentration. This is the usual standard representation of the cell. So very important part, that is the oxidation reduction of ions based on half cell potential. Now one has to understand this particular part because the oxidation reduction reactions or the half cell potentials, which we call, it is very important to understand, because the cell potential or half cell potential we need to carry out, we can calculate the potential of this cell based on this particular concept. So let us take the example of galvanic cell. Now this galvanic cell is an electrochemical cell. Now what are electrochemical cells? As I said, that converts the chemical energy of a spontaneous redox reaction into electrical energy, that we have seen, just like a battery. Okay. Now in such devices, the Gibbs energy of the spontaneous redox reaction is converted into electrical work, which may be used for running a motor or any other electrical gadgets like heater, fan, geyser, etc. Okay, so this is our routine examples. We can put in or give the input of battery, and even we can run our mobiles, our smartwatches, and there are many other things which runs on the batteries or galvanic cell that way. Now say we have shown the Daniell cell over here. Okay, now in this figure you can see this Daniell cell. Now this Daniell cell is the one such cell in which the represented redox reaction occurs. Okay, where we have represented it, here it is. Okay, this reaction is a combination of two half cell reaction. Okay, now these individual half cell reaction on addition will give the overall reaction. So these reactions occur in two different portions of the Daniell cell. So the reduction half cell occurs on the copper electrode, while the oxidation half cell reaction occurs on the zinc electrode. Okay, these two portions of the cells are also called as half cell or redox couples individually. So they are redox couples. The copper electrode may be called as reduction half cell, and the zinc electrode, it may be called as the oxidation half cell. So we can construct the innumerable number of galvanic cells on this pattern. You can take many examples: silver, zinc, silver, copper, and there are many more based on the series of oxidation potential or reduction potential. we will see during the course of this lecture. Okay. Now, these innumerable number of combinations of galvanic cell, they can be formed on the pattern of, say, Daniel cell by taking the combinations of different half cells. Now, each of these half cell, they are consist of a metallic electrode which is dipped into an electrolyte. So the two half cells, they are connected by a metallic wire through a voltmeter, and definitely there will be a switch which is required externally. Okay, there will be an external switch. So the electrolytes of two half cells are connected internally through the salt bridge. It can be connected internally through a salt bridge. Okay, so this is shown over here. So there is an external connection through wire. Now in between you can give a switch or voltmeter, and this is externally connected by the salt bridge. Okay, so this connection is always there. Sometimes both the electrodes dip in the same electrolyte. Okay, and whenever we do so, that is both the two electrode in same electrolyte, in such cases we do not require this salt bridge. Now at each electrode or each electrode electrolyte interface, there is always a tendency of metal ions from the solution to deposit on the metal electrode and trying to make it the positively charged electrode. At the same time, metal atoms of the electrode have the tendency to go into the solution as ions, and they leave behind the electrons at the electrode, trying to make it negatively charged. Very interesting. So at equilibrium, what happens? There is a separation of charges, and depending on the tendencies of two opposing reactions, the electrode may be positively or negatively charged with respect to the solution. Now there will be a potential difference which will be developing because of this cause. Now this potential difference between the electrode and the electrolyte is called as the electrode potential. Now when the concentration of all the species involved in the half cell is unity, then the electrode potential is known as the standard electrode potential. And according to IUPAC convention, the standard reduction potentials are now called as the standard electrode potentials. So we will always deal with the standard reduction potential. However, if we change the sign of standard reduction potential, so we will get the standard oxidation potential. So it is equal in magnitude but reverse in the sign. So in galvanic cell, the half cell in which oxidation takes place is called as anode, and it has a negative potential with respect to the solution. The other half cell in which the reduction takes place is called as the cathode, and it has the positive potential with respect to the solution. And therefore there will always be existing the potential difference between the two electrode, and as soon as the switch is in the on position, the electron will flow from negative electrode to positive electrode. So the direction of current flow is opposite to that of the electron flow, which is obvious. So the potential difference between the two electrodes of a galvanic cell is called as the potential or the cell potential, and is measured in volts. And the cell potential is the difference between the electrode potential, that is we call it as a reduction potential of that particular cathode. uh, uh, you can say that it has a reduction potential of the cathode, and then you can say that the electrode potential of anode as well. So it is called as the cell electromotive force, which is known as EMF. EMF of the cell, many a times we say. So when no current is drawn through the cell, the EMF of the cell can be represented, and it is now an accepted convention that we keep the anode on the left and the cathode on the right while representing the galvanic cell. So a galvanic cell is generally represented by putting a vertical line between metal and electrolyte solution and putting a double vertical line between the two electrolytes connected by a salt bridge, which is a standard convention. Now under this convention, the EMF of the cell is positive and is given by potential of the half cell on the right hand side minus the potential of the half cell on the left hand side. You can see over here, if you see, E cell is equal to the potential on right hand side electrode minus potential on left hand side electrode. Now let us take the example of equation number 11, or the representation in given in equation 11. So copper plus silver, which is copper is in contact with the silver ion, so it is giving the copper ions plus silver. That means the electrons from the copper, these are gained by the silver, and therefore copper ions are releasing into solution, and silver gets deposited. So it can be seen that the sum of this single half cell reaction at cathode, this is happening, and anode, this is happening. So this leads to the overall reaction, and that overall reaction can be represented at this particular section, that is given by equation 11. Okay, now in the cell which is represented by equation 11, it can be seen that the silver electrode acts as a cathode here, and copper electrode acts as an anode. Now the cell can be represented overall by equation which is shown here by 14. So copper is in contact with the copper ion, silver ions are in contact with the silver, and both of them, they are separated by the porous material, that is by salt bridge. Okay, so we have now E cell is equal to E right minus E left. So in this case, you can see over there that electrode potential of the silver electrode minus electrode potential of this copper. So in this way, we can represent the oxidation reduction of the ions which are based on the half cell reaction, and their representations are that way it becomes very easier to represent. So friends, now let us try to understand what is EMF of the cell. So let us say, what is electrode potential? When an electrode, you consider any electrode which is dipped into an electrolyte solution, it will always either lose the electron or gain the electron. Now what will happen if it lose or gain the electron? Either there will be an oxidation or there will be an reduction at an electrolyte interface. So the tendency, or the such tendency to lose or gain electrons when it is in contact with its own ions, is basically called as electrode potential. Okay, so this we all know from very basics of our electrochemistry classes. Now if oxidation takes place with respect to the normal hydrogen electrode, it is called as the oxidation potential, while if reduction takes place, it is called as the reduction potential. So for any electrode, they are equal in magnitude, say the oxidation potential or reduction potential, but as I said, they will always be opposite in sign. So their magnitude will be same, but their sign will be opposite. Say for example, if I consider the say oxidation potential of redox couple is 0.5 volt, then its reduction potential is minus 0.5 volt, because the oxidation potential is 0.5, so reduction potential is minus 0.5, and these values are measured with respect to the normal hydrogen electrode. Okay, so we will see in the course of time what are these hydrogen electrodes. So if the metal electrode is dipped in its solution, or it is dipped in the solution of its own ions, and if it has the unit activity, that is the if I take the solution of say 1 molar, and the temperature is say 25 degrees centigrade or say 298 K, the electrode potential is called as the standard electrode potential, because the conditions are standard. And if the electrode involves gases, then the pressure has to be at 1 atmospheric pressure for the standard electrode potential. So the standard electrode potential will be represented by E having cap 0. So E to the power 0 will be represented as the standard electrode potential. So the potential of individual half cell, it cannot be measured, because it is a single electrode. With respect to what you will measure, isn't it? So it cannot be measured individually. You have to have some other electrode with reference to it, so that the difference can be measured. So we can measure only the difference between two half cell potentials, that gives the EMF of the cell, that is electromotive force of the cell. So if we arbitrarily choose the potential of one electrode, that is say half cell, then that of the other can be determined with respect to the first one. Okay, so that means what I would like to convey is, if say say consider a cell which is comprising of two electrodes or two half cells, the oxidation takes place at one electrode while reduction takes place at another electrode. One electrode the electrons will be released, and at other electrode the electron will be accepted. So the force which causes the flow of electrons from one electrode to the other, and because of this exchange, it results in the flow of current. It is called as electromotive force. So it is actually that force because of which the electron flows from one electrode to other. Okay, so this force actually arises because of the potential difference, and it is measured in volts. So therefore it is called as force, electromotive force, because of which the current flows. So it is taken as, always taken as, the sum of oxidation potential of one electrode and the reduction potential of the other. Say as oxidation takes place at the left hand side electrode and reduction at right hand side electrode, the cell EMF will be given by the EMF of the cell will be given by the electrode oxidation potential of left hand side electrode plus reduction potential of the right hand side electrode. Okay, now why this is so? This is so because the oxidation potential and reduction potential, they are opposite in sign, but they are equal in magnitude. So we can write the representation as the electrode potential or EMF of the cell is equal to oxidation potential of left hand side electrode minus oxidation potential of right hand side electrode, and I can represent the cell potential as reduction potential of right hand side electrode minus reduction potential of left hand side electrode. Either way I can represent. Okay, or simply the standard cell EMF will be given by the standard cell EMF is equal to standard oxidation potential at left hand side electrode plus standard reduction potential at right hand side electrode. Or simply if we say that the cell potential is the difference between the electrode potentials, or we can say reduction potential specifically if I want to say, of the cathode and anode, then the EMF of the cell will be given by particularly this equation. Isn't it here? EMF of the cell will be EMF of cathode minus EMF of anode, or EMF of right hand side electrode minus EMF of left hand side electrode. So in view of this, if I consider, so this is a standard convention. So if I consider this convention, the half cell of Daniell cell, which is represented over here, the half cell of Daniell cell can be represented by these equations. That is equation number 21 and 22. Why? Because see, at left hand side electrode, this zinc uh, basically it is going into the solution. It is releasing two electrons. Zinc electrode is releasing two electrons, and therefore zinc ions are going into solution. And what is happening at right hand side electrode, at this particular electrode, they release two electrons. They are being absorbed by the copper ions from the solution, and the copper is being deposited at the copper electrode. Okay, so therefore it can be represented by this left hand side half cell and right hand side half cell. Okay, so if I sum up these two equation 21 and 22 half cell reactions, so the overall reaction of the cell will be represented by this, wherein you can see over here again, zinc electrode is releasing two electron, thereby zinc ions are going into solution, and the released electrons are absorbed by the copper, and therefore these copper ions are getting converted into copper atoms, and it is being deposited at the copper electrode. So the overall reaction is given by this Zn plus copper 2 plus, leaving Zn2 plus copper as deposited material. Okay, so basically all in all, if I want to summarize this overall EMF of the cell, the EMF of the cell basically is the EMF of right hand side electrode minus EMF of left hand side electrode. So if I say now by convention, I know that at right hand side electrode, if I consider such Daniell cell of zinc and copper, so my cathode will be of copper and anode will be of zinc, and the standard EMF I know, it is actually reduction potential is 0.34 volt for copper side or right hand side, and zinc reduction potential is minus 0.76 volt. So if I take this EMF, if I would like to calculate the EMF of the cell, it will be E right minus E left. So if I substitute this value, that is 0.34 volt minus of 0.76, so their summation will take place. So it will be 1.10 volt. So the EMF of such Daniell cell will be overall 1.10 volt. So in such way, I can utilize these conventions to find out what is the EMF of this cell. Okay, so we can actually see in the coming lectures how this concept, this EMF of the cell can be calculated, and with respect to standard hydrogen electrode also how it can be calculated. Okay, so friends, we will stop here in this lecture, and we will continue in our next lecture with the standard concept of standard hydrogen electrode and the EMF of the cell. Thank you.